A few surf spots on Earth are so legendary that surfers dream their whole lives of catching a wave there. Like there's Peahi in Maui, Hawaii, which has one of the fastest and largest waves in the Pacific Ocean. It's so extreme that its nickname is Jaws, after the movie. Then there's Praia do Norte in Nazaré, Portugal. It has the largest waves ever surfed. These monsters can get 30 meters high and don't even look real in some of the photos of them. All these waves are made by physics, of course, and scientists are trying to decode the secrets of exactly how they form. Because many of the best surf spots are currently threatened by environmental changes, and understanding that formula could help scientists preserve them, or even allow for us to design some sick waves from scratch. When you think of a surfable wave, you might picture something like this. The top or crest of the wave curls over to create what's called the barrel, and when the wave crashes in on itself, you get that foamy whitewater spray. Surfers generally surf on the shoulder of the wave in front of the barrel, or if they're skilled enough, in it. That's called getting tubed. And while it's easy to define a wave's anatomy, it's trickier to say what makes a surfing wave good. For one, it depends on the surfer's skill level, and every surfer is gonna have their own preferences. So rather than using language to define a perfect wave, scientists use a different tool. Math! To be clear, they're not trying to define a singular platonic ideal of a wave. Rather, they want to use math to define a range of waves that surfers deem good. One approach distills waves into 4 fundamental parameters. The height, defined by measuring the wave from its crest to its trough. The length, that's the horizontal distance of a single breaking wave. The peel angle, which is the angle between the crest and the whitewater, and the breaking intensity, ranked in one paper on a scale from medium to extreme. Love that the wimpy waves don't even get to be in the study. We don't care. From here, you can determine a wave's surfworthiness by considering what kinds of surf maneuvers are possible for waves created with different parameter ranges. And within a surf-worthy range of wave parameters, scientists can get to work reverse engineering the physics factors that lead to those good waves. This is complicated by the fact that waves are kind of like snowflakes. No two break exactly alike. But waves in the same location with similar formation conditions tend to look a lot alike. So scientists can still trace backwards to discover the factors that made them in the first place. To find these baby waves, we must venture far out to the open ocean in super deep water, thousands of kilometers away from shore. Now, far from shore in the deep open ocean, water picks up the energy that eventually forms waves. Most waves start when wind blows across the water, creating small pockets of underwater circulation that slowly march forward. This is called trochoidal motion, and it's also what makes buoys or ducks bob on the water. Stronger winds, say from a storm, can transfer more energy to the water and create bigger waves. This is why when there's a hurricane that's like just far enough off the coast, surfers will decide to go to the beach. Once the waves accrue enough energy, they graduate to swells. Swells have a wavelength of about 300 meters. That's like 3 soccer fields or like 100 longboards. These swells, with their long wavelengths, can actually outrun choppy waves with shorter wavelengths, helping them survive the long trek to the nearest coast. The fun stuff happens when the swells finally get to the coast and hit water that's about half as deep as the swell's wavelength. So like 1.5 soccer fields or like 50 longboards deep. This is probably not helpful. When the water gets shallow, the bottom of the wave drags along the seafloor and slows down. But the top of the wave keeps all its momentum and continues forward, which causes it to trip over itself, eventually forming crests that break. If we're lucky, the wave will break in just the right way to be surfable. But that depends on the shape of the seafloor, called bathymetry. To be surfable, a wave needs a non-zero peel angle. Otherwise, it's called a closeout, where it breaks all at once. To avoid closeouts, the beach needs to be uneven, so that one side of the wave breaks first, creating a peel angle. This is why so many famous surf beaches are also coral reefs. Basically, if you want an interesting wave, you need an interesting beach. Scientists looked at the bathymetry of 34 locations known to have good surfing waves, and they identified the seafloor configurations that created them. Then, using computer simulations, the scientists studied how these configurations affected wave direction, speed, and shape. For example, they found that dips in the seafloor seafloor can make waves faster or more intense. And the angle of the seafloor slope relative to the coast can affect whether or not waves travel in the optimal direction for surfing. So thanks to that data, scientists have basically solved the mystery of how bathymetry leads to good waves. But it's still only one part of the equation. To get a great wave, everything else needs to be just right too. That includes wind speed and direction, swell period and height, and tide conditions. So over time, experienced surfers develop intuition for the weather and water conditions that forecast the waves they like. But those conditions are rapidly changing as more surf breaks are threatened by rising seas, coastal erosion, and coastline development, all of which affect the bathymetry and coastline shape. A 2017 study found that California, for example, could lose 34% of its surf breaks by the end of the century. Unfortunately, the same strategies that protect coastlines can inadvertently ruin great surf breaks. Like replenishing an eroding coastline with extra sediment can change the bathymetry enough that waves break in totally unsurfable ways. That's why these mathematical models of surf breaks are so important. Scientists can help design interventions that preserve both coastlines and surf breaks. One way is to arrange special sandbags, rock, or concrete into underwater structures that direct sand to settle in certain patterns. These structures can reduce erosion to protect the coast and shape the bathymetry so that waves break in surf-worthy fashion. Narrowneck Reef in Australia tried this strategy in 1999 and got it to work. Scientists could even someday use these surf break models to turn unsurfable beaches into top-tier surfing destinations. For example, Middleton Beach in Albany, Australia used to only generate closeout waves on its shores. Until July 2025, when the beach debuted an artificial reef. They leveraged beach measurements and computer simulations to modify the seafloor so that it funnels waves in just the right way for them to break at just the right speed. These discoveries are certainly making waves in the physics community, and while surfers will continue to debate the definition of a perfect wave, at least now they can format their arguments in mathematical terms.